Thank you everyone for joining us today, and welcome to GOWIN'S webinar series. Today's presentation will be going over GOWIN'S USB 2.0 Compliance and Solutions Update. My name is Andrew Deuteronic with GOWIN, and I'll be your moderator. Grant Jennings, our Director of International Marketing, will be your presenter today. Please feel free to send us questions via our question or chat button throughout the presentation. We will answer those at the end. Now for a brief overview of GOWIN Semiconductor. GOWIN was founded in 2014 and our executive headquarters is located in San Jose, California. Our operational headquarters is located in Guangdong, China. We have over 160 people employed in R&D, engineering, and administration. We serve the low to mid-range density markets for FPGA needs, from 1,000 LETs to 100,000 LETs. For more information about GOWIN Semiconductor and our latest innovative products, please visit us at gowinsemi.com. At this time, I would like to start our main presentation.
Hello, key technologists, developers, and engineers of the world. My name is Grant Jennings from GOWIN Semiconductor, and I'm very pleased to present the USB 2.0 Compliance and Solutions Update webinar. Let's get started. Here's the agenda today. We're going to go over the USB 2.0 IP and what it has to offer. Then we're going to go into the compliance information provided by the USB-IF. And then we'll go into IPs and IP core generator, reference designs, development boards, and various solutions and success stories that we've seen over the past year. But first, I want to highlight just 3 key benefits that you're going to see as a reoccurring theme regarding having a USB interface integrated within an FPGA. The first is that you have a very flexible chip that can be a replacement source for your current existing USB PHY, device controller, or host controller ICs. The second is the opportunity to integrate between solutions that use a PHY, a MCU, and an FPGA within the same system. All of those can be integrated into a single chip. And the third is having the ability to interface or bridge between one interface to and from USB. Around this time last year, GOWIN announced its USB 1.1 and 2.0 PHY and device controller IPs. Since then, we've added a ton of information, which is what this webinar is really about. We've also received compliance on the USB 1.1 and 2.0 PHY and device controller IPs, such that you can utilize the USB interface in high production, high volume applications. So just to highlight what this webinar is going to be going into depth on is all surrounding the USB 2.0 PHY and 1.1 PHY IPs, as well as the device controller IPs and receiving its compliance. And then it will go into additional solution stacks surrounding USB, as well as success stories that we've seen for customers. In terms of the PHY and device controller IP, there's another webinar that's available on YouTube that goes through a little bit lower level of what is available there at the fundamentals. But this is going to go a little bit further into what all we have to offer since last year. So as I alluded to, in order to have a product go to production that has a USB interface, you have to use an IC that has that USB 2.0 or 1.1 interface certified by the USB-IF. And you can go to usb.org and you can look up if a chip has been certified or not. You'll see GOWIN Semiconductor on there, and you'll see that we are compliant for USB 1.1 and 2.0 for our PHY and our device controller. And so we announced that at the beginning of this year. We had our testing performed by a third-party design house, which is Granite River Labs, highly renowned and respected in the compliance testing industry. And we have a full report, and all of that is available directly or through the USB-IF. What they validated or ran compliance on was our Arura and LittleBee devices, which includes the ASSPs, the U2X and U2U ICs from GOWIN, which are ASSPs for USB to peripheral interface bridging, which it bridges from UART, I2C, JTAG, SPI, and GPIOs. So yeah, if you need more information, you can either look it up on usb.org on the compliance, or you can ask GOWIN sales directly. So if you've used GOWIN FPGAs before or played with our EDA tool, you'll know that it comes with a free IP core generator. This IP core generator allows you to choose a variety of free of charge, free of use IPs, configure them for however you want to use them, and then generate an IP core that can be instantiated in your design very easily. So for USB, we have a variety of IP cores that are either already available or are coming very soon. The first group is our USB 1.1 PHY, 2.0 PHY, and our device controller, which works with 1.1 or 2.0 PHYs over a UTMI interface. That's available now and is integrated into the current version of GOWIN EDA's IP core generator. The second group is our USB audio class controller, our USB video class controller, so UAC or UVC, an MJPEG encoder, which is oftentimes used with our USB video class controller, and an HSIC controller. These are all actively available. Just ask your GOWIN sales if you're interested. But it will be integrated into IP core generator in Q1 of this year, so by the end of the month. And then the third group is IPs that are upcoming and will be available in Q2 and then integrated in Q3, which is our USB 1.1 and 2.0 host controller, as well as our ULPI to UTMI converter for MCUs. And then lastly, I'm excited to hint at some new solutions coming forward in Q2, which will be related to our USB 3.0 and 3.1 solutions. So look forward to more information on that in Q2 of this year. Now I want to talk about reference designs, which are example projects to enable you as a developer to get started more easily. And I'm just going to fly through this list because we have several of them for USB. Contact your sales or rep for more information or access to these. We have a USB to peripheral bridge, converting USB to GPIO, SPI, UART, I2C, JTAG. And then we have a 5X version of that, which allows you to have 5 of those peripheral interfaces as a reference design example. We have a video pattern generator to UVC example. Essentially, it allows you to plug in a USB, have the device be a USB device, and then it throws a video pattern from a pattern generator module and shows up on your computer as a webcam. So that kind of gives you the starting point that you have video access in the FPGA. It's going to your computer. Now you can replace that as a starting point for your own video over USB project. We have a Type-C power delivery reference design. So this can be used in conjunction with the USB PHY and device or host controller IPs. And you can provide power delivery if you decide to do a Type-C interface with it. We have USB audio class to and from I2S. So really good example there. I'll show a demo of that later. We have CSI2 to UVC, Universal Video Class Bridge reference design coming at the end of this quarter. Just waiting for some new boards on that one. And then we have UVC over USB 3. There will be more information on this in Q2, so stay tuned. Very excited to talk about that in Q2. Development boards. Development boards allow you to evaluate a particular function, such as USB, without spinning your own PCB. And we have a variety of boards available. We have our USB U2X programming dongle, which leverages our USB to peripheral ASSP. We have a USB 2.0 development board, generic development board. Currently version 2 is available in limited quantities, and then a version 3 is coming. That's a cost-reduced version of the same board, and that's available in Q2. We have our CSI2 to USB 2.0 UVC camera module coming in Q2. It's a very small, less than an inch by an inch camera to USB dongle board, or a module board, kind of like a webcam, for a reference platform as a webcam. And then we have our USB UAC audio card coming sometime in around Q3, which I'll show a demo of something pretty similar using two boards, but allows for a audio input and audio output using the USB audio class, kind of like a USB audio card. But not only do you need the compliance, the IPs, the reference designs, and the development boards to create a solution using a USB IC, you also need the drivers. And not only do you need the drivers, but ideally you use the native drivers available for common operating systems. Not all ICs do, and this can lead you into trouble when you're using a proprietary driver that doesn't have its source available or is not native to the OS. Native drivers are generally always better unless there's some very unique feature. And we support open drivers as well. So for Universal Video Class on Windows, we support the native driver. Universal Audio Class, we support the native Windows driver. Virtual COM port, we support the native driver. And then for all of the peripherals, they need something that there's no native driver for them. So we use GOWIN USB, which is a very common Windows driver for doing data transfer when there's not a native OS driver available, and it's based on libUSB, which is a Linux driver that's been around for a long time. Same with the Linux side. So UVC, UAC, Virtual COM port, all native OS drivers. And then for the peripherals, we use libUSB. So there's some connection there in how those work and those drivers. So those are very common drivers. They're open. The libUSB and GOWIN USB are open drivers, so you don't have to worry about getting stuck with a particular, like a proprietary driver, and that's definitely one of our advantages in the driver space. Now let's transition into some real-world examples, some success stories, and some demonstrations of all of the stuff we discussed earlier. But before we do that, let's just reiterate those key benefits that I wanted to kind of highlight out of this webinar, which are utilizing the USB solutions offered by GOWIN for chip integration, taking multiple chips on a board that are combined to create one solution and integrate them into a single FPGA. USB interfacing and bridging, going to and from a USB interface. And then USB host and device replacement and enhancement, meaning you replace the PHY or device controller IC with an FPGA-based device or host controller IC, and then leveraging that to create new enhancements on your product over time. With that in mind, let's first look at the USB audio class to and from I2S example. Here we can take data from a I2S microphone or a I2S analog to I2S converter chip, and buffer that data, pre-process it, and then send it to the Universal Audio Class Controller IP, Device Controller IP, and USB PHY IP. Then that can be transmitted out to a PC through a USB cable. And then that can be used to record microphone data on your PC. Similarly, the other path is possible and can go from the PC all the way through to the USB PHY device controller and UAC controller, post-process if needed, buffered, and go out the I2S controller to an I2S amplifier, where it can be amplified and sent out a speaker or a headset. Here is a demo of the Universal Audio Class solution.
In this demo, we use a GOWIN FPGA along with a USB 2.0 PHY device controller and a UAC link layer to take audio data from a USB host, such as a PC, and send that data to the USB device. In this case, we use a GOWIN FPGA, convert it to an audio interface, I2S, and drive it by an external amplifier, which is then passed to a speaker. The USB audio class demo utilizes two boards. First board is a DK USB 2.0 development board, and this is connected to the USB host, in this case PC. Using a USB cable and a USB port on this board also contains the FPGA, which will contain the USB 2.0, device controller, and UAC link layer. This board has a GPIO header, which is used for a ground between the two headers. To add to this, there's an I2S clock and an I2S data line. These lines are connected with flyer wires to the audio amplifier board, which has its own header on it. This also contains an audio amplifier as well as a 1/8 inch audio output jack. Here I am programming the audio amplifier board. Next, I used the U2X dongle on the DK 2.0 board and programmed it. Here's where I plugged in the headphone jack and connected the USB cable to the PC. Now that you have everything plugged in, you'll be able to see the GOWIN UAC device in your sound settings. You could set the HZ level through the advanced settings, and then you'll see the audio levels while playing a song or video on your PC. You can see how the levels go up higher and the song builds up more. Thanks for checking out our UAC to I2S audio demo, and have a great one.
Now that you've seen the demo of the Universal Audio Class solution, here's just a success story using Universal Audio Class. So we had a customer who was using 3 ICs. They were using an FPGA for front-end audio processing, and they needed that because of the performance and the DSPs provided in the FPGA. And then they had a communication interface to an MCU that did some post-processing and also had the USB interface via ULPI. And then they had a ULP to USB 2.0 bridge for the final USB interfacing. And so we replaced that solution with a GOWIN FPGA, providing all the functionality of all these chips. So the DSP usage and the performance utilization of the FPGA combined with our processor IPs, either the hard Cortex M3 and the GW1 and S4, or the soft ARM Cortex M1, or even our RISC-V soft cores. In this case, they use the GW1 and S4, and they use the Cortex M3. Then we had the universal audio class controller, device controller, and USB 2.0 interface for the rest of the design, creating a single chip solution for this application. Next, we have our CSI2 to USB 2.0 reference design. This reference design takes a MIPI CSI2 camera, brings that into the FPGA using our MIPI CSI2 IP, receiver IP, and then optionally uses our image signal processing pipeline and MJPEG encoder to improve the image quality from the raw image sensor capture, and then compress the video stream down by 10x or so. And then that compressed data is buffered and then runs to the universal video class controller, device controller, and USB 2.0 PHY. Here in the bottom left-hand corner, we have a preview of the USB video class module that will be coming out in the near future in Q2. And very small form factor, and it will be able to showcase this particular demonstration. To show our starting point and our color bar generator reference design, here's a demonstration of a design using the color bar pattern generator, the universal video class controller, device controller, and USB 2.0 PHY to provide a great starting point for enabling USB video applications on FPGAs.
GOWIN now offers USB 2.0 IP cores, which include the USB 2.0 PHY IP as well as the USB 2.0 device controller IP. These IP cores can be used to stream data to and from a USB host, such as a PC. As a result, this can be combined with a universal serial bus video class handler, as well as an input video stream to stream video over USB 2.0. Here we have a video pattern generator, just passed to a UVC or USB video class handler. This packages the data and packets to the USB 2.0 device controller IP and then transmits over the USB 2.0 PHY. This example is using a pattern generator to provide the video stream, but this can be replaced with a video interface such as MIPI CSI2, MIPI DPI, or MIPI DVI to provide the image sensor interface directly streamed camera or image sensor data through a USB 2.0 pipeline. Here we have a demonstration of driving a video pattern over USB 2.0 using a GOWIN USB 2.0 development board. Pattern generator generates the video stream, which is passed to the UVC handler, then passed to the device controller, and finally transmitted out with a USB 2.0 PHY, all done in a single GOWIN chip. In this example, we are transmitting a 480 by 320 YU-VU video stream at around 79 frames per second. This is aligned with the maximum isosynchronous data rate of around 192 megabits per second of streaming video data. Depending on the application need, this can be combined with compression methods to increase the resolution or frame rate even further.
Now let's look at a success story. We had a customer case come in where they were using 3 ICs to go from MIPI CSI2 or multiple CSI2 cameras to a USB 2 interface. And basically, it's very similar to the other case. We came in and offered the capability of bringing that down to a single chip to do the MIPI CSI2 interface, the buffering, the image processing. In some cases, this case didn't need it, but we could do the compression, and then provide that USB 2 interface to do a single chip solution of the exact same thing. Let's take a look at our image signal processor demo, because this IP can sometimes be very valuable to use in conjunction with the Universal Video Class Controller IPs to provide front-end image processing and offload that from the downstream processor or SoC.
With GOWIN releasing the Image Signal Processing Pipeline, or ISP, we wanted to show a demonstration of how GOWIN's ISP improves image quality by going over a few different IP cores. The first IP core shown here is the CFA, the color filter array. We have a 5x5 color filter array, which gives a higher quality image compared to a 3x3 array, which is often used. The CFA utilizes the current pixel that is available and interpolates the other pixels. For example, if you have a green pixel, it interpolates the red and the blue based on the adjacent pixels surrounding that green pixel. The next IP core demonstrated will be the color correction matrix, or CCM. The CCM adjusts the gain and offset of the imaging stream. What this means is that the CCM will adjust the gain on the red, green, and blue components. Not only that, it adjusts the influence of one color component onto the others. For example, if you're adjusting red, you are not only adjusting the gain of red, but also adjusting the gain of red on the influence of green and blue colors. This makes a big difference in video quality, since as photodiodes increase in luminance, they are affected by the other color components. The CCM ensures that these coefficients calibrate the image processing pipeline upon startup. Another feature of the CCM is that it includes an offset control for each color component. Next up, we have the gamma correction IP, which has two major functions. Gamma correction compensates the way our eyes react to different color components over the illuminance, and secondly, it compresses the imaging data into a smaller number of bits per pixel. For example, if you're using a 10-bit image sensor but are using a 24-bit RGB output, you would want to compress each color component from 10 bits to 8 bits. For our last IP core, we'll be going over the auto exposure and auto white balance IP core. Auto exposure adjusts the exposure level based on algorithms which determine how bright or dark an image is. If the image is too dark, it will adjust and brighten the image to the correct level. Auto white balance compensates for each color component so that the white you are seeing will remain white. In this demonstration, we will see how the image processing pipeline is paired with a microcontroller to process the auto exposure and auto white balance modules in real time. This is achieved using a histogram and statistics engine, which looks at the overall luminance level and exposure of each pixel. When an image goes through an image processing pipeline, it will affect the way white is shown. Oftentimes, white will become off-colored after going through the CCM or CFA. Auto white balance ensures that the white is balanced and remains white. This is done frame by frame by the MCU to calibrate the correct exposure and white balance of the image to compensate any variance created during the image processing pipeline.
To demonstrate a good USB to peripheral bridging example, I look no further than our latest GOWIN programming dongle, which bridges USB to JTAG, I2C, GPIOs, and SPI. And we're going to show here us programming GOWIN FPGA, but you can use this dongle and the U2X IC or the reference design for USB to peripheral interfaces to program other FPGAs, MCUs, SPI flashes, or control for any project really through the GPIO interface. Let's take a look.
Today I will be walking you through programming our new U2X programming dongle. Once you have the software installed, you want to pull up the U2X programming dongle user guide on the GitHub repo. This will have step-by-step instructions on how to install drivers on your U2X programming dongle and how to program it using GOWIN EDA. First, we want to install the driver using Zadig. You can locate a link to download this tool through the U2X dongle user guide. Next, plug in your U2X programming dongle and open Zadig. You will be able to see the device listed by clicking List All Devices. Choose the GWU2X option listed and install the driver. I see a reinstall option here since I already had the correct driver installed beforehand. Once you have the driver installed, go ahead and open Device Manager and make sure you see the GWU2X dongle under the USB option. With the programmer open and the dongle and the board plugged in, you'll be able to click USB cable setting, then query, and then save. From there, go ahead and use the scan option within the programmer and choose the correct board you are using. Once this is all set, double-click under Operation and use the SRAM Program option to choose the correct bitstream to program your board. I'm using the bitstream from the UVC module LED project, which is uploaded on the GitHub repo. You'll want to grab the .fs file for your bitstream. In this example, I'm programming the LED to blink on the board. Once the bitstream is set, hit Program, and your board should have the LED blink.
And yay, now it's time for the giveaway. So we're giving away 20 of these dongles that you just saw in action. All you have to do is follow the link that will be provided in the chat box and the message, the secret message that is also provided in that chat box. If you do that, you'll be one of 20 lucky winners, and I'm excited to see how you use the new dongles. Okay, let's look now at how some of the new upcoming IPs are being utilized. The first is USB host, which is used in a few different ways. One is for hubs, because in a hub, you need a PHY and device controller to interface from where the PC or whatever it's connected to. And then you need a bunch of USB device controller and PHYs on the other side to multiplex out. So we've seen that a lot. We've also seen the USB host connected to a ULPI interface to provide that bridge interface for microcontrollers and SoCs. We've also seen this in conjunction with the new HSIC IP for doing hubs, where you'll have the HSIC IP used as the interface to, say, a processor or an SoC, and then that branches out into many different device and host controller plus PHY interfaces. So all these variances of hubs, host, device controller, HSIC, they're all kind of used in conjunction together to multiplex data off of multiple ports. And then lastly, the ULPI interface, which I kind of mentioned, is used in conjunction with a USB host or device controller and PHY on the other side to provide that USB interface to devices that don't have the PHY but have a ULPI interface to connect an external USB IC. And also we've seen some things where, most of the current bridging ICs with ULPI interface, they only go from ULPI to 1 or 2 host controller ports, whereas in our case we can go to anything. We can do multiple device controller ports, multiple host controller ports, you name it, we can do it. It's just that flexible solution. Here we're just showing an example of a hub solution using a USB host, multiple devices, multiple HSIC interfaces to create a unique hub solution. And here we're just illustrating the use of the ULPI or SRAM interface to USB 2.0 bridging solution to provide a USB interface on an MCU that only has a ULPI or SRAM interface. For human interface device controllers, we've seen a variety of different usages. You can think that there are a lot of new types of printers and CNC type machines where you need that USB interface, and a lot of times it's not direct until now because you don't have the right controls on the other end. So there's been a lot of that type of application. Also, a lot of replacements in this area with very legacy USB controllers on things such as printers, and being replaced with the FPGA that has a lot longer lifetime and can be enhanced and repurposed over the years as needed. Here we have another one of those integration solutions where we've taken multiple ICs in a system and integrated it into one FPGA that previously wasn't possible. So in this case, we had a customer that was using a small FPGA for peripheral control, and then they used the MCU for processing of that control and sensor input. And then they were using a USB IC for the USB interface because the MCU didn't have one built in. And so we just combined all that into one FPGA because we have the ARM Cortex processor, which was they were already using a Cortex M processor. We have the USB interface, and then we have the FPGA that they were already using anyways. So great solution, huge cost reduction, easier to develop, and much more reliable having one chip instead of three. And just to illustrate an example where the FPGA for peripheral control could be highly valuable is in multi-channel PWM. So a very simple case, PWM is just modulating IOs, but MCUs are limited in the number of channels they can process reliably, and SoCs need a dedicated ASIC to do PWM. So oftentimes there's some external ASIC that does a peripheral to PWM conversion, and a lot of times if you think of just like a printer or a CNC mill, some sort of or a robot arm or something like that, all of these things just use servos, and they need a lot of servos, and they end up going to a small MCU or SoC just for that USB interfacing. And so FPGAs can do PWM very, very well. They can do it on any IO, and they can parallel process that PWM. So whether it's an LED array, whether it's many servos for a industrial robot control arm, or whether it's some sort of power control for some complex power system or power management, these are all possible as a single chip solution with a USB interface now. And here's a customer success story of just that. So we had a customer that was using an SoC which only had one PWM output. It only had, it had two IOs that were capable of doing PWM, which wasn't enough because they needed to drive up to 16 servos. And so they used a I2C to PWM IC bridge as an ASIC bridge. And we just combined those in multiple forms. So they really didn't need an SoC. They were just utilizing it because they could have everything. They could run scripts and everything on that SoC. But once they found that they could just go from USB to PWM, they just took all those scripts and ran them on their very small PC anyways. So and they also still utilize the SoC through a USB interface. So this just provided them a lot of better options for doing the USB to PWM conversion directly, and then they could reutilize all of the same scripts and code they were using before, either on the SoC or on the PC directly. So I ultimately hope through those examples, demonstrations, and use cases that you can see the three key benefits that I've been mentioning coming out very clearly. That integration of multiple chips into one is now possible with having that USB interface in the FPGA. That all sorts of new USB interfacing and bridging use cases are now possible, as we're not dictated by an ASIC that may or may not be available anymore. And then the USB host replacement and enhancement is a critical factor for end-of-life parts and also having alternatives, as well as improving the capabilities and having the flexibility of more interfaces or less interfaces from the same chip over time.
And that brings us to GOWIN Design Services. This group specializes in reviewing project requests and developing custom solutions to make them a reality. You should see a link shared in the webinar chat. If you have a project you need developed, please visit GOWIN Design Services and submit your needs to GOWIN and start developing your project with us today. We also wanted to share some additional resources. I highly recommend following us on our social media platforms. You'll be able to have access to the latest news and products as soon as they're available. Next, we have a list of reps and distributors for parts and development boards. We have a wide variety of third-party boards as well, such as Magic Jelly Bean, which is constantly expanding with new projects and products. And lastly, we have links to the software needed for any of our devices and products. You can download GOWIN EDA and GOWIN's MCU Designer directly from the GOWIN site or through these links here.
So that concludes the USB compliance and solutions update webinar from GOWIN. I hope you enjoyed it. I hope there was some learnings, and I hope that you're thinking about some new ways to interface your devices or your projects based on utilizing GOWIN FPGAs with the USB PHY, device controller, host controller, HSIC, universal video class, universal audio class solutions that we have to offer, and really looking forward to helping you go win by programming for the future. Thanks.
All right, thank you, Grant, for that presentation. We're moving to the Q&A portion of the webinar. Please send us your questions and we'll answer them now. If we happen to run out of time, we'll answer those questions through email. All right, first question here. Can I connect any type of video interface to the USB UVC video solution? For example, can I create a low resolution HDMI DVI RX to USB 2.0 converter? Could I interface multiple cameras to one USB interface for stereo vision application?
Yeah, so good question. The answer is yes. You can connect any video stream really to the USB UVC interface. There are some limitations on resolution. USB 2.0 goes up to 480 megabits per second once it's encoded. So the bandwidth is a little bit lower than that, about 20% overhead, 20% lower than that. But video, I think you can get up to about 720p or so, or VGA, and then after that you can use MJPEG compression, and we have the MJPEG encoder that can get you up to as much as 4K 30. So depending on the resolution that you're looking at, you can definitely do it, and it's pretty common. And then for stereo vision cameras, you need to sync up the cameras or virtualize the channels for the two cameras. So either way is possible. If you're using line buffers for that, then you can do that in the FPGA using block RAM. In cases where you need to convert the frame rate, say you have an HDMI input at 60 frames per second, but you want to transfer that over USB to at 10 frames per second. We do have the GWR series devices, which have up to 8 megabytes of additional memory, which is often used for frame buffering. So either way, we have devices that have the memory extension for frame buffering, some of these cases, if you design them correctly or optimally, you can just get away with line buffers. And on the USB UVC interface, normally you're packetizing that data as you want to stream it. So normally line buffers are okay. But yeah, and we have the HDMI RX IP available, an IP core generator, and I believe we have some dual camera reference designs as well as the interface IP for various cameras such as CSI2 or DPI.
All right, thank you. Next question. What is the difference between the U2X ASSP and the USB to JTAG SPI I2C reference design?
Good question. So last year, around this time last year, I believe, we introduced the U2X and U2U ASSPs. And this is the start of a variety of application-specific ICs that we're offering at GOWIN. And so the U2X converts USB to either SPI, JTAG, I2C, or GPIO, and then the U2U device just converts USB to UART for programming or controlling various things or MCUs. And the difference between this and the reference designs is that the reference design is basically the same type of design, but is in an FPGA that allows you to use as a reference point or example design to add additional features. So let's say that you really like the U2X device, but instead of just one port, you wanted 5 ports. Well, we actually have a reference design for that, going from USB to JTAG, SPI, or I2C, and you can choose out of those 5 ports which one is what interface. And then you could adjust that accordingly. Or if you wanted to do USB to JTAG, SPI, or I2C plus UART, you could do that. So that's the difference. One is more you just put it on your circuit board and go. And the other one is you want to design something custom and use the example design or reference design as a starting point.
Awesome, thank you. Next one. What is the benefit of using USB 1.1 versus USB 2.0?
Okay, so we offer both the USB 1.1 and a 2.0 PHY for the physical interface. We also offer a device controller that can do 1.1 or 2.0, and it's parameterized accordingly to which one you choose. So 2.0 can go up to 480 megabits per second, and 1.1 is around 12 megabits per second. So quite a bit of speed difference there. So why would you want to use one versus the other? Well, a couple reasons. 1.1 at 12 megabits per second uses less logic resources than the 2.0 IP. So you can get it into a smaller FPGA, which means that it's going to reduce cost if you don't need that bandwidth. So, and a lot of times you don't need that bandwidth for things like JTAG, SPI, or I2C, or even HID or PWM applications. But for something like streaming video or high resolution audio, then you kind of need the 2.0. And most of the time, those applications, it's okay to have a little bit more resources used. The difference is pretty small. It's only like, I think the last time I looked, it was like maybe 20% difference in logic resources. So not a huge difference, but in some cases, it can be the difference between between two devices. Also on 2.0, from a PCB design perspective, you're starting to get up into that hundreds of megahertz type range. And so 1.1 is a little bit more forgiving in terms of your PCB design. It's a little less things to consider. And also the board design's a little bit in terms of passives and things like that is a little bit simpler. So just things to consider, just depends on the application and what you're trying to do.
All right, next question. Is it possible to create a hub or repeater design that allows me to hub multiple USB devices, but then also add additional peripheral control?
Yeah, so the answer is yes. Between the USB host controller design and the USB device controller design, you can utilize both of those to make a USB hub. We kind of saw that in the one example. And then in the one example, there's the HSIC port. That HSIC is kind of an internal USB type interface specification, and it's used to reduce the cost inside onboard chip-to-chip communication with USB. So it's kind of like USB without the CDR-based PHY. So that is kind of a unique hub. That hub example is kind of unique, and that's kind of an example of being able to design a hub but do something a little bit different that may not have a ASIC or a SoC type device that is either available or it would be too expensive to do with a larger chip. So yes, you can do a USB hub design and then have a port off of the side on another channel that's doing UART or I2C or even PWM. Or you could even be snooping the line for some sort of test equipment application.
Next question we have, do drivers load automatically, or do I have to write any code for the drivers?
Excellent question. So yes, in most cases, depending on the application, drivers will load automatically. So if you're doing UVC, since we use the native drivers associated with Windows OS or Linux OS, those drivers should see the device identifier and load accordingly. Same with Universal Audio class. Like we saw in the audio demo, those drivers use the driver that is available and is native to Windows OS and just loads automatically. Same with HID. The HID solution uses native drivers. The only ones you have to worry about, Virtual COM port does also. So doing UART through USB with a virtual COM port driver, that is also a generic driver. In the case of WinUSB or LibUSB, this is when you're running into cases where there's not really a general purpose use case associated with it. And in this case, you would use the library and driver, the libUSB driver, to develop your calls, your data receive and data transmit calls using that driver and using that C or C++ API. So generally, yes, I think for most cases, and it's just only if you're doing corner cases with particular conversion interfaces. And most of the time you need special software. You're designing something custom and you have to design it appropriately in those cases.
Okay. Next up, I have, is there a full spec for the USB audio solution? Number of channels, sample rates, bit depth, and is it synchronous?
Yeah, so another great question. The USB solution, I believe that there will be some documentation for. It's still pretty early. We just have the demo and kind of the demonstration video. It's pretty easy to use and pretty straightforward. I think the documentation will complement it very well. In this case, we just have, it just shows up as an audio card. It has the PHY device controller and then UAC link layer stack. And then that goes with some buffering to I2S controller to drive the I2S amplifier. Similar, but other path going the other way for the microphone. And in terms of going beyond that in terms of like multiple mics and things like that, it's a reference design. So you have to add that, you know, we may do some reference designs with multiple mics, with multiple outputs, but that will take a little bit of time. So the answer is yes, coming soon. If you need anything, please let me know. I can probably get you the appropriate materials accordingly. They just may not be available online yet.
Awesome. Next up, we have, is there any possibility for multiple USB to multiple UARTs? For example, 8 to 10?
Yeah, so if you wanted to do USB to multiple UARTs, I think a great place to start would be that USB to 5-channel output design. I'm not sure if it includes your UART. I think that each of the ports is configurable to JTAG, SPI, I2C, GPIO, and maybe UART, but they're each configurable. So you can have one as JTAG, one as SPI, one as I2C. And we also have the USB to UART design. So I think between the combination of those two should be pretty straightforward to update accordingly. And then just to answer the question, yes, absolutely, you can have many UART channel outputs, which I've seen some use cases come in, particularly for like doing heavy programming. So there's some cases we've found where for certain companies, they've been doing, you know, building up devices over many years, and they'll have a computer with like tons of USB programming cables hanging off of the USB ports, and they all get kind of messed up. So having a USB to multiple UART device reduces those USB ports and you know, makes it a little easier on the OS. So definitely possible. Definitely have some good reference and example designs for you. Just talk to your sales or message us after, and we'll get you set up with that.
Excellent. Next up, I have, are there any plans to support Mac OS drivers?
Yeah, so Mac OS, I believe that, well, there's two pieces to this. So if you wanted to use any of the native drivers with Mac OS, I believe that most of those cases Mac OS has native drivers for, and they should be compatible. So like Universal Video Class, Universal Audio Class, these are kind of like the drivers that are used for an external audio card over USB or a webcam over USB. So those should connect automatically. Same with Virtual COM port. That one should have no problem with Mac OS. And then it's just the custom solutions. If you're going to use libUSB, I believe, and I just did a quick search here, it looks like libUSB is supported. You know, Mac OS is Unix based, so it doesn't surprise me there. I don't think that there would be any problems, and we'd be happy to help you get through that if there is any. But you should be able to use the libUSB driver for Mac OS and do the same thing that you would do with Linux or even Windows OS with the Win USB alternative. Good question.
Okay, and it looks like I have one more for you. The demonstration that you did for the USB to audio I2S seemed to use the Arura. Would that work on the LittleBee FPGA that is also present on that eval board?
Yeah, so the USB audio, or sorry, the USB DK USB board, it has both an Aurora and a LittleBee on it. And the reason for that is that we wanted to show compatibility with both devices, as well as make sure that we had a board that could have a board for each, as some of the internal physical interface capabilities in terms of serializers and deserializers are a little bit different between those devices. So there's no reason why a solution on Aurora for USB 2.0 won't work on LittleBee and vice versa. I think we just chose Arura in this case during development time to have a little bit more room and flexibility for things such as GOWIN logic analyzer captures and things like that. So yeah, no reason, just have to watch the resource utilization, but you're looking at, I think all the resource utilization from the webinar last year has the PHY and the device controller. You're looking at about 2K LUTs for that, and then the audio class link layer is probably another, no more than another K. So under 3K LUTs for all of that, I would say including the I2S controller as well, probably both. So if you wanted to do just that solution that we showed, it's probably a 3K lookup table solution, taking a guess. But yeah, that would fit in the Arura, the LittleBee 4K, the GW1N4, the 1NS4, if you wanted to use the processor with it, the hardened Cortex M3, or the 9K as well, up to the 9K, if you wanted to do some additional processing there. So definitely.
All right, looks like that is all for questions. Thank you everyone for participating in today's webinar. A recorded video of this presentation will be available by tomorrow, and you'll be sent a link directly to the email you used to register. This concludes the webinar. Thank you, stay safe, and have a great one.